Hi guys, a very good day to all. Myself Karthika. Hope all are doing good. So in our last lecture, we have discussed about top-down parsers. So top-down parsers is nothing but it tries to perform parsing starting from the starting symbol and until it reaches the input string. So it does the parsing from top to bottom. So today we are going to discuss about bottom-up parsers. So under top-down parsers, we have discussed about predictive parsers and recursive design parsers. And we have also discussed a simple example of how a predictive parser accepts a string. In our today's class, first we are going to see about bottom-up parsers. So bottom-up parsers is opposite to top-down parsers. It tries to perform the parsing starting from the input symbol until it reaches the starting symbol. So it is a reverse of our top-down parsers. So bottom-up parsers are categorized into shift-reduce parser, then LR parser. The LR parser is again categorized into SLR, CLR and LALR. In this lecture, we are going to construct a shift-reduce parser and also a simple LR parser. So the agenda of our class is, first we are going to check how a shift-reduce parser works. Then we are going to see about the various types of LR parsers and the steps of how these LR parsers can be framed, followed by a simple LR parser. Let us see this in detail in our lecture. Shift-reduce parsing is a type of bottom-up parsers. It tries to construct a parse tree starting from the input string until it reaches the starting non-terminal symbols. Majorly, shift-reduce parsers uses four types of operations like shift operation, reduce operation, accept operation and error operation. Let us discuss about these operations in detail. Shift-reduce parser, since it is a type of bottom-up parsing, it constructs the parse tree from leaves to the root, and it also uses two unique steps. The steps are known as shift step and reduce step. Shift step. The shift step refers to the advancement of the input pointer to the next input symbol, which is called the shifted symbol. This symbol is pushed onto the stack. The shifted symbol is treated as a single node of the parse tree. Then in reduce step, when the parser finds a complete grammar rule in the right hand side, it replaces it to the left hand side. So that step is known as reduce step. So this reducing takes place when top of the stack contains a handle. To reduce, it uses a pop function. So the pop function is performed on the stack. So what is meant by pop function? It popping of the symbol that is present at the top of the stack. So in reduce step, a pop function is performed on the stack and this pops off the handle and replaces it with LHS non-terminal symbol. Then other basic operations are accept operation. So accept operation is nothing but if only start symbol is present in the stack and the input buffer is empty, then the parsing action is called accept. When accept action is obtained, it means successful parsing is done. So accept means successful parsing. Error. This is the situation where the parser can neither perform shift action nor reduce action and not even accept action. That condition is called error. For performing these types of operations, that is shift operation, reduce operation, accept operation and error operation, when a parser finds no correct symbol, no matching symbol, the parser requires basic data structures for performing it. So one is a input buffer. So the input buffer is for holding the input string, the one that we need to process. Then it contains a stack. Next is a stack. The stack is used for storing and accessing the production rules. Then we have seen about handle. So what is mean by handle? Handle is a substring that matches the body of the production and whose reduction represents one step along the reverse of a rightmost derivation. Okay. So handle pruning is nothing but A rightmost derivation in reverse is known as handle pruning. So if a handle is there in the top of the stack, that is replaced by the suitable production by our shift reduce parser. Now let us see an example of how a shift reduce parser is used to check whether a string is accepted or not. So the grammar we have taken is S gives capital C, C gives small c capital C, and C gives small d. So this is our grammar. The input that we are going to take is C, C, D, D. So we are going to check whether our shift reduce parser for the following grammar is capable of accepting this string or not. So initially the stack contains a starting symbol $, and the input buffer contains the input string C, C, D, D followed by an end marker $. So this $ is used to indicate whether the string has come to an end or not. Now first action is shift action. We have to shift C into the stack. So shift C. So now C has been shifted, pushed into the stack. The remaining input is C, D, D, $. See, if the input operator has more priority than in the stack, then we have to perform shift operation. In stack, operator has same or less priority than the priority of incoming operator, then we have to perform reduce action. Okay, shift action is nothing but simply pushing the symbol into the stack, and reduce option is nothing but we need to reduce that particular symbol with the equivalent production. So now while comparing both inputs small c and small c, so they are having less priority, so I am going to shift next C. So $small c, then here DD $. Next I am comparing the top of the stack containing small c and the top of the input is also containing D. So both symbols are having same priority, so we undergo shift operation. So I am going to shift D. So $CC D, here a single D $. Now you can check this small d. For this small d we are having a production. So C gives small d. So this D, terminal D can be reduced to capital C. So I am going to reduce D to C. So now this small d will be popped out of the stack and it is replaced with the corresponding capital C. Now what is in the input? D $ is in the input. Next I will compare the symbols that is in the top of the stack. So in the top of the stack we are having a non-terminal symbol, so it has more priority than the input. So I will try to reduce this non-terminal with any equivalent production. So if I check the next symbol below the top, we are having terminal C. So terminal C and non-terminal C can be replaced with this production. C gives terminal C and non-terminal C. So I am going to apply reduce production. So I am going to apply reduce action. So small c and capital C will be reduced to capital C. So simply you pop these two symbols out of the stack and replace it with the equivalent production. In the input we are having D $. Now again if I compare the top of the stack, we are having non-terminal symbol. So this non-terminal symbol has higher priority than the input present in the input buffer. So I am going to apply reduce action. Before applying the reduce action, you go and check whether there is any equivalent production with this non-terminal C. No, there is no equivalent production with this single non-terminal C. So I am going to compare with the next symbol that is present in the stack. The next symbol that is present in the stack is small c. So for small c and capital C, we are having an equivalent production. So I am going to apply reduce action. Reduce small c and capital C with capital C. So I simply remove these handle and I replace with capital C. So this is called as handle pruning. Then in the input we are having only D. Again I am checking whether any production is there with non-terminal C. No, there is no production with a single non-terminal C. So I need to apply shift action. So what I have to shift? I need to shift D. So shift D. So D is pushed into the stack. Then again, I will compare whether any production is there equivalent to D. Yes, we are having a production equivalent to D. So I am going to apply reduce action. So reduce D with capital C. So I pop D and replace it with capital C. Then I will check whether any production is there equivalent to a non-terminal symbol. No production is there equivalent to a single non-terminal C. Then I will check with the next symbol that is present in the stack. The next symbol is another non-terminal C. Then again I will go and check with the production whether there is a production equivalent to two non-terminal C's. Yes, we are having a productions equivalent to two non-terminal C. So I am going to apply reduce action. So we are going to reduce two non-terminal C with a non-terminal S. So both non-terminal C will be popped out and it is replaced with the non-terminal S. So finally we have obtained our starting symbol. So we have started with the input strings. After processing all the input strings, finally we have obtained what? We have obtained our starting symbol. So our input is finally accepted. So this is called as shift reduce parser. By this way, a shift reduce parser checks whether a given input string is accepted or rejected by the parser. LR parsers. LR parser is a non-recursive shift reduce and bottom-up parser. It uses a wide class of context-free grammar which makes it the most efficient syntax analysis technique. LR parser is also known as LRK parsers, where in LRK, L stands for left to right scanning of the input string and R stands for construction of the rightmost derivation in reverse, and K denotes the number of look ahead symbols to make decisions. So there are widely three algorithms available for constructing a LR parser. That is simple LR parser, then LR parser, then look ahead parser. So these are the three types of LR parsers. Now let us see in detail about these parsers. So simple LR parser. So simple LR parser works on smallest class of grammar. So it has only few number of states and the table length is very small, and it is a simple and fast construction parser. Then LR parser. So LR parser works on complete set of LR1 grammar. It generates large table and it has large number of states. Since it contains large number of states, the construction process is very slow. Then look ahead parser. Look ahead parser works on intermediate size of the grammar, and here the number of states are same as in simple LR parser. So this LALR, that is look ahead LR parser, is an efficient parser. So now let us discuss some differences between LL parser and LR parser. So LL parser, what is mean by LL parser? LL stands for leftmost derivation. So it does a leftmost derivation, whereas RR parser does a rightmost derivation in reverse order. And LL parser starts with the root non-terminal on the stack, whereas LR parser ends with the root non-terminal on the stack. Then LL parser ends when the stack is empty, whereas LR parser starts with an empty stack. Then LL parser uses the stack for designating what is still to be expected, whereas LR parser uses the stack for designating what is already seen. And LL parser builds the parse tree in a top-down manner, whereas LR parser builds a parse tree bottom-up manner. And LL parser continuously pops a non-terminal off the stack and pushes the corresponding right-hand side production, whereas LR parser tries to recognize a right-hand side on the stack, pops it and pushes the corresponding non-terminal. LL parser expands the non-terminal, whereas LR parser reduces the non-terminal. LL parser reads the terminals when it pops one of the stack, whereas LR parser reads the terminals while it pushes them onto the stack. Then LL parser follows pre-order traversal of the parse tree, whereas LR parser follows post-order traversal of the parse tree. So these are the difference between LL parser and LR parser. Now let us see in detail about SLR parsers, simple LR parser with an example. So simple LR parser is otherwise called as LR0 parsers. And the steps for constructing SLR parser is, first we need to construct an augmented grammar, then we need to form a closure set, then we have to compute goto, then you have to perform action definition, then you have to construct a parsing table, and finally you have to implement a stack for processing the input. So these are the various steps involved in construction of SLR parser. Augmented grammar. So what is mean by augmented grammar? See, consider the grammar G where S is the start symbol. So the augmented grammar of G is G dash. If a grammar G is there, the augmented grammar is G dash. So this G dash will have a new start symbol S dash, and we introduce a production S dash tends to S. So that is called as augmented grammar. That is, we add one more production to our existing grammar. That is called as augmented grammar. We are augmenting one more production. Next step is you have to form closure items. So in formation of closure items, two types of items are there, kernel item and non-kernel item. So kernel item is nothing but it is a collection of items where S dash gives dot S, and all the items whose dots are not at the leftmost end. So that is called as kernel item. Okay. In non-kernel item, so this is a collection of items in which dot or the left end of the RHS rule except for the augmented grammar. Okay. So in kernel item, the dot is not at the leftmost end, whereas in non-kernel item, the dot will be in the leftmost end except the augmented grammar. So that is the difference between kernel item and non-kernel item. So the next step is we have to form these kernel items and non-kernel items. Next, closure function. So closure function is nothing but let I is a set of items for a grammar G. Then closure of I is computed using the following steps. Initially, every item in I is added to closure of I. Initially, we add all the items into the closure. See, consider A gives X dot BY. So, this is nothing but an item in I. Then B gives Z, it is a production. Now, what we need to do means, we need to add this item B gives Z to I. So, if I add, it becomes A gives X dot BY. So, the production of B should be added to I. Okay. So, this rule has to be applied till no items can be added to closure of I. So, simply saying, you just check with the non-terminal symbol. If to the right of the dot, if a non-terminal symbol is there, you need to add the production of that non-terminal symbol to the closure. Okay. Next, goto function. See, consider an item in I. A gives X dot BY, then goto of I comma X will be A gives X B dot Y, including closure of B. Okay. So that is called as goto function. Okay. So while looking into the example, you can understand better about the closure function and goto function. So now let us take an example. The same grammar, S gives CZ, C gives small c capital Z, and C gives D. So this grammar we have taken. So what is the first step in SLR parser? We have to find the augmented grammar G dash. Augmented grammar is nothing but adding one more grammar to our starting symbol. So what is our starting symbol? S is our starting symbol. So the augmented grammar is S dash gives S, and the remaining productions you write as it is. So S gives non-terminal C's and C gives terminal C followed by non-terminal C, and C gives D. So this is a augmented grammar. Then what is the next step? We have to form the closure function. So for forming the closure function, we have certain rules. Okay. So before that, for the augmented grammar, what is the augmented grammar? This is our augmented grammar. So for this augmented grammar, simply place a dot in the leftmost end. Okay, so I am just going to simply place a dot in the leftmost end. For all the production, I am going to place a dot. See, why we are placing a dot means dot represents how many symbols we have looked out. Okay, see here for this production, if a production is like this means it means we haven't seen any symbol. If a dot is moved to this place, it means we have seen one symbol. And if a dot is moved to the end means it means we have seen all the symbols. So dot represents how many symbols we have seen already. Okay. So this first step is you have to form a closure named I0. I0 is formed by placing a dot at the leftmost end of all the productions, including the augmented grammar. Okay. Then for forming the further closure functions, we need to follow certain rules. The rules are, you first shift the dot one place right in each iteration till it reaches the rightmost end. For example, if a dot is present here, in each iteration you have to shift this dot one place to the right. So in the first iteration the dot will be shifted here. In the second iteration the dot will be shifted here. So likewise you have to shift until the dot reaches the rightmost end, right? Then consider the symbol after the dot after one shift. After each and every shift you have to consider the symbol after the dot. Okay, see here, this is my initial production. After shifting, after first iteration, my dot has moved here. So after every shift you have to consider the symbol that is to the next of the dot. To the next of a dot, if it is a terminal symbol, you simply start. If there is no symbol means, for example, if the dot has come to the rightmost end means, you have to write left recursive to end of the production and repeat shifting of dot. If it is a non-terminal symbol means, you have to include all the corresponding productions of that non-terminal. Okay, so these are the rules to be followed while forming the closure function. Now using these rules, let us form the closure function for this I0 closure. So this is our I0. So I0 is S dash gives dot S and S gives dot CC, C gives dot CC and C gives dot D. So this is our I0. Okay. So first let us take the first production. In this first production I need to shift the dot. So while shifting the dot, what symbol I will view? I will view non-terminal yes. So I am going to undergo a go to with respect to the non-terminal yes. So if I undergo shifting action, how my dot will be shifted? It will be shifted one position in the right side. So my dot will be shifted one position right side. So it becomes S dot. So finally my dot has come to the rightmost end. So further no more shifting takes place. So let me name this closure as I1. Okay. Now considering the second production, S gives dot CC. So first I am going to perform a shift with respect to the terminal C. So if I perform a shift with respect to terminal C, how my closure will be? S gives, how my dot will be shifted? S gives C dot C. So after every shift you need to check the symbol that is present after the dot. After the dot, what symbol we are having? We are having a non-terminal symbol. If there is a non-terminal symbol, what we have to do? You have to include all the respective productions of that non-terminal symbol. So what non-terminal symbol we are seeing? Capital C. So you have to include all the respective production of the non-terminal symbol capital C. What are the productions? This and this are the two productions with respect to capital C. So include these productions. C gives dot C, capital C, C gives dot D. That's it. Now let me name this closure as I2. Okay. Next, take the third production for this production I am going to shift with respect to small c, because the symbol that is present next to dot is a terminal symbol. So I am going to shift with respect to terminal c. So if I shift, the dot will move one position right. So it moves here. After shifting, you have to check the symbol that is present next to dot. Next to dot, we are having a non-terminal symbol. If there is a non-terminal symbol, you have to include all the productions of that non-terminal symbol. So what are the productions for C? C gives dot CZ and C gives dot D. Okay. So this is not similar to any of the closures. So I am naming this closure as I3. Next, for this production, I am going to undergo a shift with respect to the non-terminal D. So if I undergo a shift, how my dot changes? It moves next to D. So it moves next to D. So our dot comes to the rightmost end. So no more further recursive shifting and all. So this has reached to the final state. I name it as I4. Okay. You have to continue this process until our dot reaches the rightmost end. See here, I1 reaches the final state and I4 reaches the final state. Now I2 and I3 have to be recursively shifted once again. Now in I2 we are having how many productions? 3 productions are there. So let me consider the first production. First production is respect to what? Is respect to the symbol that is next to the dot. So next to dot, what symbol is there? Non-terminal C. So with respect to non-terminal C, we are going to undergo a shifting operation. So shifting operation is nothing but moving the dot one position right. So I am going to move the dot one position right. If I move, dot moves to the rightmost end. That's it. So it has reaches the final state. So let me name this state as I5. Next, the second production is small c. With respect to small c, I need to undergo shifting. So if I undergo shifting with respect to small c, it becomes C gives dot, C dot capital C. So a non-terminal symbol is there next to dot after shifting. So you have to include all the productions of this non-terminal C. What are the productions of that non-terminal C? C gives dot CZ and C gives dot D. This closure is equal to our I3. I3 and this are same, no. So I am simply combining both. So this is equal to I3. Next we are having a production C gives dot D. So I am going to undergo a shifting with respect to D. If I undergo a shifting with respect to D, so the dot moves next to D. So it has reaches a final state and this is equal to what? This is equal to our I4. So I am combining this. Next, so we have completed for I2 all the productions we have undergone shifting. Next let us come for I3. In I3, for the first production, I need to undergo a shifting with respect to capital C, that is non-terminal C, because the symbol that is next to the dot is capital C. So we have to undergo a shifting with respect to the symbol that is next to the dot. Okay. So with respect to C, if I undergo a shift, my dot moves one position right. So my dot moves one position right. So it has reaches the final state. So no more further shifting. So let me name this state as I6. And again for the second production of I3, if I undergo a shift with respect to small c, it is equal to what? It is equal to C gives C dot C, and again I have to include all the productions of C. So that is equal to dot CZ and C gives dot D. That is equal to what? That is equal to our I3 only. So simply I am putting a loop here. And the next production is C gives dot D. So if I undergo a shift with respect to D, it is equal to what? It is equal to C gives D dot. That is equal to I4. So simply I am putting a loop to I4 if I undergo a shift with respect to D. That's it. So we have obtained final states and no more further shifting. Our dot has come to the rightmost end. Now using this closure functions, we are going to frame a passing table. So for framing the passing table, we have certain rules. That is, passing table is denoted by T, where S is the shift operation and R is the reduce operation. Then next step, you have to give number to the productions. Then you have to fill the table entries, action and go to. So for filling the table entries, action, for filling the action, the terminal symbol is there. For example, go to of I0, A. If it goes to I3, then you have to mark the table entry as S3. That is shift operation. Shift 3. Okay. In RHS, if we found a dot operator at the end, and if it is an augmented grammar, what is mean by augmented grammar? S dash gives S is an augmented grammar. If a dot operator is in the rightmost end and if it is an augmented grammar, then for this grammar, table entry of $1, for the table entry $1, you need to mark accept. If it is not an augmented grammar, for example, if we have a grammar like this, S gives the A dot, where dot is at the rightmost end. So if a go to is like this means, and if it reaches to the state, and if the state marked as I3 means, what we have to do means, you have to find the follow for S. And for all the follow terminal symbols, you have to fill the reduce action. You have to fill with the corresponding production number. Okay. If for example, if the corresponding production number is 1 means, you have to fill all the follow symbols with R1, R1, R1. Okay. So these are the steps to be followed for filling the action table. And for filling the go to, so go to entries will have state numbers like 1, 2, 3 and so on. And go to entries indicate the transition of a state. See, for example, in a closure I4, C gives D dot. So this is our transition closure. So first we have to find follow for C. See, for example, follow of C is equal to C, D and dollar means what in the table entry, table of 4 comma C, what you have to write means you have to write with the respective production. So C to D dot is what production? It is production number R3. So you have to write with the production number. Then T of 4 comma D is equal to R3 and T of 4 comma dollar equal to R3. So the C, D and dollar are nothing but the follow symbols. Okay. For all the follow symbols, you have to write with the respective production number with the reduce symbol or. Now let us go to our example. So we have determined our closure function. We have to frame our passing table. So first let us mark the states. How many states we have obtained? 0, 1, 2, 3, 4, 5 and 6. So totally we are having 6 states. So mark the numbers starting from 0. 0, 1, 2, 3, 4, 5 and 6. Then under action you have to fill the terminal symbols. So what are the terminal symbols there in our production? Small c, small d and dollar or the terminal symbols. So you write the terminal symbols. Then what are the non-terminal symbols available in our production? Capital S and capital C are our non-terminal symbols. Because our productions are S gives CZ first production and second production C gives small c capital C and third production C gives D. Okay. So with respect to the productions, the terminals, the non-terminal symbols are S and C. So in action you have to represent the terminal symbols follow with a dollar and in go to you have to represent the non-terminal symbols. Now check what is 0 comma C. What is 0? State 0 to capital C. Where we move? We move to I2. We move to the state I2. So if a go to action takes place, if a go to takes place with respect to a non-terminal symbol, you have to simply represent the state number. So I0 comma capital C goes to which state? It goes to the state 2. So simply represent 2 here. Okay. Then I0 with S. I0 comma S. So it moves to which state? It moves to the state I1. So write 1. Okay. So if we are making a shifting with respect to a non-terminal symbol, you have to write only the number of that states. Okay. Whereas if we undergo a shifting with respect to a terminal symbol means you have to write what? You have to write the number of the state along with shift operation. Okay. Now what is 0 comma small c? I0 comma small c. So it is a terminal symbol. So it goes to which state? It goes to the state I3. So how you have to write? You have to write as shift operation, that is S3 you have to write. Then C to 0 to D. 0 to D, I0 comma D. It goes to which state? It goes to the state I4. So you have to write like S4. So we have already seen in the rules. Next I1. I1 comma. I1 is our final state and it is an augmented grammar. So for I1 comma 1 comma dollar, you have to always fill with accept. Since it is an augmented grammar and it is in the final state, for the augmented grammar, you have to always fill the table entry 1 comma dollar as accept. Next 2. For I2 state, I2 comma. What is capital C? Capital C goes to the state I5. So, I have to write it as 5. And for I2 state, with respect to a terminal C, it moves to which state? It moves to the state I3. So, how we have to write? For terminal symbol, you have to write it as a shift operation, S3. Then I2 to terminal D, it moves to which state? It moves to the state I4. So, you have to write it as S4. Okay. Next, for the state I3. From I3, a shift with respect to the non-terminal C. Non-terminal C goes to which state? It goes to the state I6. So, write 6 in the go to state. Then I3 with respect to terminal C, it goes to which state? It goes to that state itself, that it is goes to I3 itself. So, I have to write it as S3. Then I3 with respect to terminal symbol D, it goes to which state? It goes to the state I4. So, write it as S4. Okay. Then coming to the state I4. I4 is what? I4 is our final state. From final state, there is no more transaction. There is no more shifting operations. For the final state, first you have to find the follow. So, now let us find the follow for this symbols. What is follow of S? Follow of S. S is a starting symbol. So, follow of S is dollar. Then S is not there in any RHS. Then you have to find the follow for C. What is follow for C? Follow for C. C is present here. So, follow for C is what? C itself. So, if it is a non-terminal, you have to find the first of C. So, what is first of C? C and D is our first. Okay. And also, C is present at the rightmost end. So, if a non-terminal is in the rightmost end, you have to check with the symbol in the LHS. In the LHS, we are having S. So, the follow of S is also follow of C. So, what is follow of S? Dollar is the follow of S. So, it is also a follow of C. So, C, D and dollar is follow of C and dollar is follow of S. So, now coming to our state I4. In I4, we are having the non-terminal C. So, for non-terminal C, what are the follow symbols? C, D and dollar are the follow symbols. So, for all the follow symbols C, D and dollar, you have to write the production number using reduced state. Okay. So, what is the production number of C gives D? Production. So, C gives D is third production. So, you have to write it as R3. R3. R3 for all the follow symbols. Next, I5. So, for the state I5, what we are having? We are having C dot. So, C dot is what? C dot is our first production. So, you have to write it as the production number along with the reduced symbol or symbol. So, production number is first production. So, R1, R1, R1. Next, for the state 6, I6, we are having C gives small c, capital C, and this is what production? This is our second production. So, I have to write it as R2, R2, R2. Okay. For the non-final states, you have to represent it with the shift operation, and for the final states, you have to represent it with the reduce action. Okay. The reduce action will be represented by means of the production number. So, finally, we have framed our passing table. So, usually using this passing table, we are going to check whether an input is accepted or not. Now, let us process for the input CD, CD. So, initially our stack contains dollar and our input contains our input followed by the end marker. So, now first it starts with the state 0. For 0, in the stack we are having 0 in the top and then the input we are having C. You go and check what is the action 0, C. So, 0, C, what is the action? It is S3. So, S3 means you have to shift 3. That is, you have to push the symbol number onto the stack. Along with the input symbol, you have to push the symbol number also. So, what is the input symbol? C is the input symbol. Along with that, you have to push the symbol number. What is the symbol number? 3. You have to push 3 here. Okay. Always you have to maintain your top of the stack with a number. Now, what is the top of the stack? 3 is the top of the stack. And what input we are having? In input, in the top we are having D. So, go and check what is 3, D. So, 3, D is equal to S4. It is a shift operation. That is, you have to shift the symbol D along with the number. What number? 4 is the number. Now, what is the top of the stack? 4 is the top of the stack. And what is the top of the input? C is the top of the input. Now, go and check what is 4, C. So, 4, C is equal to R3. It is reduce operation. So, reduce operation means you have to go and check with our production. Is there any equivalent production to reduce the symbols that is present in the top of the stack? So, in the top of the stack, what symbol we are having? We are having D. So, this is a number. You should not consider the number. You should consider the symbol only. So, in the top of the stack, you are having D. So, whether is there any production that can replace D? Yes, we are having productions like C gives D. So, we can replace D with capital C. So, I am going to replace D with capital C. So, while reducing it, you have to pop the number value also along with that symbol. Along with the symbol, you have to pop the number value also. So, I am just popping out D and 4 and I am replacing with capital C. Okay. Already I have told that always you have to maintain a number in the top of the stack. Whereas after reducing, we are having a symbol in the top of the stack. So, we need what? We need a number. So, in order to maintain a number in the top of the stack, what I am going to do means, I am going to check the number that is below the top of the stack. So, below the top of the stack, we are having a number 3. So, you go and check with the table what is 3, C. What is 3, C? So, 3, C is 6. So, you just push that number into the top of the stack. Now, our stack is maintained. That is, the top of the stack is containing a number. Now, again compare with the input. So, in the input what we are having? We are having small c. So, go and check what is 6, C. So, 6, C is equal to what? It is equal to R2. R2 means you have to replace with the second production. What is our second production? C, small c. So, you go and check into the stack. So, first we are having capital C. Then, in the below we are having small c. So, I am going to reduce these symbols with the capital C. So, I am going to reduce small c, capital C with capital C production. I am going to reduce, I am going to pop all the symbols along with the numbers and push the respective non-terminal symbol. So, after popping out, what I need to push? I need to push capital C. In the top of the input, we are having C, D, $. Now, again our stack is violated because always the top of the stack should contain what? It should contain a number. So, for containing a number, what I am going to do? I am going to check the below number that is present in the top of the stack. Below C, we are having 0. What is 0 comma c? 0 comma c is 2. So just write 2 into the top of the stack. Now the top of the stack contains 2 and the top of the input buffer is small c. Go and check in the table what is 2 comma c. So what is 2 comma c? 2 comma c is S3. So you have to shift the symbol c along with the number. So c is shifted into the stack. So c along with the number, what is the number? 3 is the number. Now the top of the stack contains 3 and the top of the input buffer contains D. So go and check what is 3 comma D. So 3 comma D is equal to S4. So again you have to shift the next input symbol along with the number. So what is the next input symbol? It is D. What number we have to insert? 4. Okay. Now the input buffer contains dollar only. Now go and check what is 4 comma dollar. So 4 comma dollar is equal to what? Is equal to OR3. That means you have to apply reduce operation. You have to reduce with third production. What is our third production? C gives D is our third production. So simply you have to pop D along with the number and you have to push the non-terminal C. So I am going to pop D along with the number and I am going to push non-terminal C. Now the top of the stack is not containing a number. So go and check the number that is below C. Below C we are having 3. What is 3 comma C? So 3 comma capital C is 6. So just insert 6 into the top of the stack. What is 6 comma dollar? 6 comma dollar is equal to what? Is equal to OR2. That is you have to reduce with the second production. What is our second production? Terminal C and non-terminal C has to be replaced with the non-terminal C. Okay. So terminal C is here, non-terminal C is here. So this has to be replaced with non-terminal C. So I am just removing that and I am replacing it with non-terminal C. So now again in the top of the stack we are not having a number. Go and check the number that is below the top of the stack. So below the top of the stack we are having 2. So what is 2 comma capital C? So 2 comma capital C is 5. So push 5 onto the top of the stack. Now the top of the stack contains 5 and the input buffer contains dollar. Go and check what is 5 comma dollar. So 5 comma dollar. So 5 comma dollar is equal to OR1. That is you have to reduce with first production. What is our first production? Non-terminal C and non-terminal C has to be replaced with non-terminal S. So non-terminal, both C and C has to be replaced with non-terminal S. So dollar, 0 and yes. Okay. Now our top of the stack is not containing a number. So go and check the number that is below the top of the stack. Below we are having 0. So what is 0 comma S? 0 comma S is equal to 1. So just push 1 onto the top of the stack. Now what top of the stack contains? 1. What input buffer contains? Dollar. So go and check what is 1 comma dollar. So 1 comma dollar is equal to what? It is equal to accept. So finally our string has been accepted by our SLR parser. So these are the various steps involved in SLR parser. So SLR parser is a simple left-right parser. So in SLR parser, the first step is you have to frame an augmented grammar. Augmented grammar is nothing but adding one more predictions to our grammar. Then after framing the augmented grammar, you have to find out the closure function. So closure function is nothing but first you have to put a dot at the leftmost end of all the predictions. Then you have to apply goto function. Goto function is nothing but shifting the dot one position right. You have to shift the dots until the dot reaches the rightmost end. So you have to continue this process until the dot comes to the rightmost end. And for every shifting operation, you have to check the symbol that is present next to dot. If next to dot is there a non-terminal symbol, you have to include all the predictions of that non-terminal symbol also to our closure. So by this way, you have to form all the closure functions. After forming the closure functions, you have to construct a parsing table. So the parsing table contains two things to be filled, that is action and goto. So in case if it is not a final statements, you have to represent it with a shift operation, that is S operation. Then if it is a final statements, you have to represent with a reduce operation, and that reduce operation will be followed by a number. That number is nothing but our prediction number. So we have to represent it with a reduce operation. By this way, we have to fill the passing table. After filling the passing table, using that passing table, you process our input and check whether the input is accepted or not by an SLR parser. So these are the various ways of constructing an SLR parser to accept a input string. Okay guys, hope you understand about a simple LR parser and how a string is accepted by SLR parser. So in our next lecture, let us discuss about the other types of LR parser, that is CLR parser, nothing but canonical LR parser, and LA-LR parser, that is look-ahead LR parser in detail. Meet you all in the next lecture. Bye-bye.